Okay, well, happy Friday, everybody. I'm glad you're here. Review of where we are and what's going on here. So, as you see, I'm in my announcements. And today, don't forget, quiz 5 tonight is due. So, if you haven't done that, at least one attempt, get on that ASAP. Hopefully, your homework is done, the corresponding homework. And then we've been working on 7.5 and we've started 7.6 and we're going to continue with that today, do some homework problems, and then move on to kind of a quick look at the quiz that's due on Monday, quiz number 6. And as you can see, homework 7 and 8 for next week are already available. I'm not saying you have to get in them now, but they're there for any of you who want to go forward a little bit. And then, of course, quiz 7 is due next Friday, a week from today, and then quiz 8 will be due Monday, like always. So, um, let's see where we are here. Sorry, right here. All right. So we're talking in section 11.6. So let me go backwards a little bit just to make sure those of you who forgot or missed the other day, we're talking about a number of formulas here in 7.6. Okay, they're still dealing with your trig. You're still going to have identities and solving and graphing and all that, but these are just going to be formulas to help you break it down a little better. So the main thing I want you to remember of these three, these are called the double angle formulas, and as you can see, it's because the inside of each trig function on the left has a 2 theta, double of what it normally is. And there are some of these where you're definitely going to use the sine of 2 theta. For the cosine of 2 theta, as you see, there's three formulas. We broke these down last time. You don't have to know them all. If you know the first one, you can kind of create the other two with the Pythagorean identity. You know, replace cosine square or replace sine square, and you get the other two results down here at the bottom. Okay, so normally in my class, I say you have to know at least one of those, and you have to know the sign. For you guys doing your quizzes and tests online and homeworks, you really just have to have these formulas written down somewhere and accessible. And as kind of a quick reminder, we have learned a number of identities. We've learned a few theorems. We've got more formulas today and even more after this. My recommendation is have them all on one sheet of paper. Might not be easy to type them, but handwrite them on one sheet of paper, and you always have that one sheet of paper with you. You also should have, if you have not yet memorized it, but you should be close, all your angles written down. And I don't just mean the angles, talking about the sine and the cosine of each, and most importantly, the radians, because that's mostly what we're going to deal with. Okay, now a lot of the 7.5 and the 7.6 sections, because we're doubling and having our angles and doing things with the angles, you'll see a lot of examples with the degrees, and that's mainly just to give you a better, quick understanding of them. But all of these formulas, realize they do apply. You know, if I have a pi over 3 and I want to, or sorry, a pi over 6 and I want to double it, it becomes a pi over 3, this formula will work the same. All right. So moving on, we did a few examples of these. Then we'll get to the newest formulas that I kind of left class with on Wednesday. So this is, I don't want to say it's a whole lot different, but it's kind of like they've solved for the square. Okay, and as I mentioned, some of your formulas, you're going to go both directions. So this is a case of if you have a sine square, you can rewrite it as this right here. Okay, what they call this is it's a power reducing formula because you have a square function for all three of these trig functions. And by rewriting them, even though this looks a ton more complicated, there are no more powers on your trig functions. They're just regular cosines. So it's a way to break them down. So as you see me do problems, I'm going to keep going back and forth between all these slides just to show you what we're dealing with. So in this particular case here, we're going to write an equivalent expression for cosine to the fourth. Now, I like the first step right here, where they remind you cosine to the fourth is essentially cosine square being squared. And they do that so that you could see in this parenthesis, we're going to replace it with all of this right here. This 1 plus cosine 2 theta over 2. That's going to replace the cosine square. And that's what you see right here. Okay, now the next part, they're squaring it. And the other part I don't want you to forget is when you are squaring anything, whether that's a trig function or an algebraic function or whatever, anytime you're squaring some sort of a parenthesis, remember, it means that parenthesis times itself. So in the case of the 1 plus cosine 2 theta over 2, it's going to be 1 plus cosine 2 theta over 2 times 1 plus cosine 2 theta. And remember, that's not square. Those are 2 thetas. Okay, so you see, you take the 2's in the bottom, that's where they got the 1/4 from. All right, so then what they're left with, and you don't have to write this step, but I just want to show you because not everybody is seeing when they skip a step here. But that's where the 1/4 comes from. You square the 2 times the 2. That just comes out front. So now when we FOIL this, I got to emphasize, make sure you are foiling just like the first day you FOILed. It's the first times the first. It's the outer 2 terms multiplied. It's the inner 2 terms, and it's the last terms. That's what you're getting when you're foiling. So 1 times 1 is 1 for the first. Then you get the outer. It's 1 times cosine of 2 theta. Well, that's a cosine of 2 theta. That's your outer term. Your inner term, you have cosine of 2 theta times 1. There's your I. And last, you have cosine 2 theta times cosine 2 theta. This is where people start to make up their own rules. And this is where I want you to stop and realize what's going on. I have cosine 2 theta times cosine 2 theta. Now remember, if I had cosine alpha times cosine alpha, the actual written way is cosine square, same angle. Alpha, alpha, it doesn't become an alpha squared, it doesn't become a 2 alpha. If they're both identical trig functions, both of them are cosine alpha, your result is going to be a cosine alpha squared. And you put the little 2 right there. So when you see this, even though that's both a 2 theta, these are both cosine 2 theta, and that's all you get right there. That's what you put for this last term. And that's the part that really gets a lot of people screwed up on that one, is they're not sure what they mean by that. Okay? So now you add these. Let me pause here. Any questions on that? Okay, so now we're looking for similar terms. Those are both cosines. So a second ago, we were multiplying a couple cosines. That became a cosine square. Here we're adding a couple of cosines. So the answer is going to be 2 cosine 2 theta. They're identical. They have to be. Whenever you add something, they have to be similar terms. For trig, that means they both have to be the same trig function, and they both have to have the same angle. So if I had a cosine beta plus a cosine alpha, that's it. I can't combine them anymore. If I had a cosine of theta, pretend that's a theta, plus a cosine of 2 theta, guess what? Can't add them up. We're done. They have to be exactly identical in order to add them together to be similar terms. So that's why these two, which were identical, they become this 2 cosine 2 theta. All right. Then from there, let me clear out my work here so you can see the rest of this better. Now we're going to distribute. We distribute that 1/4 here, here, and here. That's how they get the 1/4 and then a 1/2 cosine 2 theta and a 1/4 cosine square 2 theta. And again, I'm going to keep bringing up these rules. You knew these rules, but everything gets a little lost when you're dealing with trig functions. When you distribute, you're only distributing to the coefficient, the front number in front of these weird trig functions. You don't distribute to the 2 theta. You don't affect the 2 theta. It's just the front number. That's where we are right now. Okay? So again, as I'm doing this, these are all based on old things and methods you know, but if there's something that just doesn't quite work, let me know, because a lot of times I can give you a quick example. I'll write one up where it's things like x's and x squares to kind of remind you, oh yeah, that's how we did it. That's the process before, and it just translates to now. So this is where we were. Now, looking at a few more things. Look and see what they're doing here. See if you can figure out the change. So again, this top thing is where we were just now. Now all of a sudden we have a 1/4, that's there. A 1/2 cosine 2 theta, that's there. Now we have this big thing. Okay? Now think about where this came from. Think about what changed. So when you're trying to follow the steps here, this is, trying to draw. That's the only thing that's different right there. Okay, that cosine square 2 theta. Well, what's it replaced with? It's replaced with all this. That's from the formula that we just had. I'll go back 2 screens just to remind you. right there. Cosine square of any angle is always going to be 1 plus cosine of double that angle over 2. So you see what they did right here. They took a cosine square. It doesn't matter what the inside is. A cosine square is always 1 plus cosine over 2, and then you double what the previous angle was. So yes, we'd already doubled it to 2. Now we double it again, and that's where you get this 4 theta right here. And then the last part, they did one more distribution. So this 1/8 goes here, and it goes here. That's this 1/8. So this thing becomes a 1/8 cosine 4 theta. This 1/8 combines with the 1/4. And just in case you don't see it, they did the common denominator. That's how they got the 3/8 right there. Okay? So everything we're getting here, oh, I'm sorry if that was the end of it. Yeah. Everything we're doing here is exactly like the first couple sections of this chapter 7. The difference is you got some new quirky formulas, and you just have to look at each formula one at a time. And remember, when you use a formula, it's a swap. It's a replacement. Just like back in the day when I told you x equals 6 and you had a function or an expression, everywhere you saw an x, you'd replace it with a 6. No big deal. So in this case, anytime you have a cosine square of something, it's always going to replace with 1 plus cosine 2 theta over 2. And that's where you go. You just wipe it out and you replace it. It's just a clean sweep. Get rid of this, put this in its place. That's what you're doing with all these formulas. And then don't look at it as, okay, where am I going with this? This is getting big. This is getting ridiculous. It is a little bit, but you don't start thinking 4 steps ahead. Okay? Just think, okay, let's do the replacement. Let's clean it up. And now every single thing you see right here after the substitution, all that is algebra. That's just going back to algebra. If you look back at this entire problem, it's all algebra. Even though it has trig functions, think about this. We did a substitution right here. Well, that's kind of an algebra move. We simplified. We FOILed. Then go over here, sorry. We replaced again, more algebra. We distributed, or we multiplied. Then we distributed. Then we simplified. It's just a bunch of algebra steps. So how you have to approach this, your mindset is not, how am I going to get this final answer? Let's just do the substitution. And then let's clean it up using our algebra rules. And you have to be a real stickler to the rules. Follow the rules. Don't make up anything. Don't wish for anything. Don't hope for anything. See what you get. And then from there, see what, then you start connecting to the very end of, okay, what am I trying to make this become? What's my goal here? And this problem, as you recall, what they were shooting for was write an equivalency of cosine to the 4th. So that's what we did right here. Okay? It wasn't exactly establishing an identity. It wasn't proving an identity. It was kind of creating a new one ourselves. Okay? So cosine square can replace with this in the future. Not that you would have this, but now anytime you see cosine 4th, it would become all this big pile right here. All right. Any questions on that example? And again, like always, we're going to get these in the homework problems, so hopefully that'll be a little more clear. So in this particular case, we have sine of, let's see, what are we trying to do here? Solve a trig equation using identities. So we have an equation, sine theta, and let me just try to show this. We have sine theta cosine theta equals -1/4. We want to solve for the theta. Find what thetas make this true. Okay, now, I'm sorry. Let me do that because I know everybody would want to know this. Real quick, we'll take a quick detour. Where do you access the slides? So go to your course when you log into My Math Lab. Video resource library is right here. And then we're in chapter 7. And always make sure you click something here. You got to click the PowerPoint. I mean, you could click it all. And then when you do the Find Now, you get all this stuff. And I'm in this 7.6 PowerPoint, and this will download every one of these. All the ones I use, you can download all of these right to your computer and look at them anytime you want. Okay? And then, of course, there's a bunch of other things. Hopefully that was what you were looking for, Kayla. Okay, so back to our slides here. So we want to solve this. Now remember, when you first learned how to solve equations, 2x plus 3 equals 9. Okay, let's make it a little more difficult. Let's make it 11. Okay, your very first day of learning is, well, let's see, does 0 work? Sorry, it's supposed to be an exclamation point there, or a question mark. Does 0 work? And then what you would do is, you would go plug the 0 in, and you'd ask yourself, does it work? You'd test it out. Okay, then we'll try 1, then we'll try 2, then we'll try -1, etc. And you see, that was the very beginning. You just plug in numbers. Now, the main reason they do this is so that you hopefully will never forget that when you find a solution, it has to be something that is true, that makes the original statement a true, the original equation a true statement. So when you see an equation like this, you can guess 0 degrees, 30 degrees, 45 degrees, 60 degrees, etc. And you would probably get lucky and get one of them, maybe both of them. Okay, maybe there's more than 2, we don't know. So that's where, just like with that equation I showed you, that's when all of a sudden it's like, okay, I'm tired of guessing. I need a procedure. Well, you had a procedure. Subtract 3 from both sides, divide by 2, and now no more guessing, you had your solution. It's the same thing here. We're trying to see if we can find a way to not just guess, but to algebraically solve these equations to get an answer. Okay, so how we're going to do this here. Sorry, let me get my mouse moving to the next step here. Okay, so left side of the equation, except for factor 2, is in the double angle formula. Okay, now this is one of these where you have to kind of see this. What we're doing in this chapter will help you, but you see how this almost looks like what we have in the equation. All right, it's close. Now, one way I could do it is I could divide by 2, so I get sine of theta cosine theta equals sine of 2 theta over 2. And I could take this, and I can completely take this and replace it into there. Now, why that's an advantage to us is it's always easier to solve an equation that has one trig function. Here we have 2, so we kind of might have to do that guess and check game. So this makes it a little bit easier, but it's like, okay, no, I don't have to do the guess and check game. I'm down to one trig function. This is going to make it a lot easier because now I can just think of, oh, what are the answers for sine? What can I get? Okay, so using a formula like that one will allow you to replace 2 different trig functions like sine and cosine with a single sine. And we used it earlier, like the other day, to get a double angle and make it into a bunch of single thetas, but now we're going to go backwards on this one. So what they suggest here is, let's multiply the equation both sides by 2. So here's my equation, multiply both by 2, and we get this. Any questions? Everybody okay with what's up here right now? Okay, so multiply both sides by 2. -1/4 times 2 is, of course, -1/2. And now we can do a clean swap, this for this. And that's why the left side now becomes sine of 2 theta equals -1/2. Okay? Now, again, you should know this. So I'm going to show you this less and less, but I'll show it here in the beginning. We're thinking, where is it that sine? Doesn't matter that it's a 2 theta. I'm looking for sine of -1/2. You've solved these before. Where is sine -1/2? Well, it's here at 210 degrees or 7 pi over 6. And it's also down here at 330, 11 pi over 6. So those are my 2 angles that are going to be equal to the inside of the trig function. So show you there. Okay, so there's your argument, your 2 theta, and we figure out that we get rid of this. Okay, now don't worry about this 2 pi k. We've done this before, but I'll talk about that a little more in a second. We just know that 11 pi over 6 is one of our solutions. Okay, so we're going to plug that in, and did I miss a slide? I'm sorry. I guess they didn't show the first one, the 7 pi over 6. It's okay. We have the 11 pi over 6, and now notice what happens is, whenever you have a trig function, all right, you know the sine of 11 pi over 6 is going to work to equal -1/2. If you add 2 pi to that, it's also going to work. If you add 4 pi, it's going to work. All these work. So basically, we're taking this inside, and we're setting it equal to what was inside before, the 2 theta. That's where this equation comes from. Okay, so it's a little different than we did earlier, but it's similar. Okay, there's multiple ways we can do this. So we divide by 2 to everybody, and you see we get 11 pi over 12 plus k, pi k pi, and that's because we divided this by 2 also. So what that means is 11 pi over 12 is a solution, along with 11 pi over 12 plus pi, and add another pi, another pi, another pi. All of these are going to work. Okay, so how we condense this down? We try it with k equals -1, and you see we get something that's not within the domain they specify. Remember, they asked for you to give solutions between 0 and 2 pi, not including 2 pi. So the first answer we got, the 11 pi over 12, that's going to work. We tried a -1, that's not going to work. So we toss that out. Here's the second one, the one I just wrote. When you try k equals 0, you get 11 pi over 12. That is a good answer. Try k equals 1. You get 23 pi over 12. Now remember, we want answers less than 2 pi. This is close, but it is less. That's going to work. Now you try 2, and this is going to be too big. And that's the process you go through just to make sure that you do have the correct ones within the domain they state. The solution set's got to be in between the given numbers, if they tell you that, which they did. So now the other answer was 7 pi over 6, and it's the same thing. 7 pi over 6 works, add 2 pi, another 2 pi, another 2 pi, all these work. So you see how they reformat this, where they say, okay, the inside was 2 theta. We set that equal to 7 pi over 6 plus 2 pi k, and solve for the theta, and we do the same thing as before. Okay, so for this answer down here at the very bottom, let's try a bunch of different k's and see what works. So they try k -1 just to confirm this is a negative and it won't work. Now 0, that works. 1, that's less than 2 pi. And if you're wondering, how do I know it's less than 2 pi? Remember, over 12, if I have 24 over 12, that's 2 pi. We're a little bit less, so that's good. Now we have something more than 24 over 12, so that's out. So my 4 solutions are 7 pi over 12, 11 pi over 12, 19, and 23 pi over 12. Okay, so you're combining some old and new. You remember a couple sections ago, we were solving equations like this that had 2 thetas or 3 thetas inside. And remember, we got multiple answers. Even if you go back to the original equation, remember that one rule I told you all in the very beginning of solving these was when you get an equation, where is it? Right here, this bottom one. Normally, any trig function, if you're trying to solve between 0 and 2 pi, most trig functions will give you 2 solutions. If you have a double angle or a square, you're going to double that, and you should be looking for 4 solutions. So that's why when we went through this whole process, 4 answers emerged. It was all because of the double theta. It just doubles the number of answers, just like a 3 theta would give you 6 answers. Okay, so now that we have that, we'll go to a little bit of a word problem here. An object propelled upward at an angle of theta to the horizontal with an initial velocity of v naught. That v sub 0, that's how fast the object was when it started outside of the cannon, when it launched. Okay? The range r, the horizontal distance at the distance that the object travels. So that's how far it is right here, from the cannon to the spot that it lands. And the function is this right here. Okay? So kind of break this down. What it's saying is that the angle is this. So the different angle is going to be different amounts. So obviously if the angle is 0, this thing's just going to hit the ground right when it comes out. If it's 10 degrees, it's going to go, but it'll probably drop. But you can't make the angle too high, because if you have a 90-degree angle, it's just going to shoot up and come right back down and get no distance. And you've all done this before when you throw a ball somewhere. You know, you have to get that perfect angle to throw it to get the furthest distance. So this angle correlates to whatever the distance traveled is. And then also what's important is initial velocity, because if you throw a ball very fast, it's going to go a lot further than if you just sort of barely chuck it out of your arm. So these two things come into play. So for step 1, they want to show that this formula equals this. Now this one's fairly easy, I think, because we're doing what we just did a minute ago. And then part B is going to be find the angle for which r is a maximum. That's going to be a little more fun. Okay, we're going to get a lot more on that one. All right, so rewrite the expression. Same formula as before. Sine of 2 theta equals 2 sine cosine. How I know to pick that is when I see sine times cosine, I want my brain to think, okay, this may be a sine double angle formula. That's sine 2 cosine right there. Okay, it's not exactly 2 sine cosine like the last problem, but we can modify it. So what did they do? They just treated this as, well, it's kind of a weird one here. They took this and rewrote it as, okay, sine cosine is the same as 2 sine cosine over 2. Why'd they put the extra 2's in here? As long as you do it in the top and bottom, it's fine. They did it so it looks like the formula above. So we can replace the top with sine 2 theta, and then this 2 becomes part of the 16, becomes a 36. So, sorry, 32, I'm sorry. So that's part A, make that equation. Part B is find the largest value for the range. What angle do you need to shoot the furthest? And this is a very useful example in real life applications. You know, if you're launching a football or a baseball or a cannon or any object, you want to know what angle should I adjust the machine at or my arm at to get it to go the furthest. Okay, so if you look at a few things here, the largest value for the sine function is 1. So go back, this is on this equation right here. We want this r to be the biggest number it can. So remember, sine is going to be the biggest when the whole thing is, this whole function is going to be the biggest when it's 1. My initial velocity, obviously, as that goes up, you're going to get higher, but we're trying to find out what angle gives us the best way to go. Okay, so sine and cosine, just this part right here. Let me make it clear. Just that. Okay, it doesn't matter if there's a 2 theta, a 1 theta, or an 8 theta inside. This box has a value anywhere from -1 to +1. We don't get anything bigger than 1 for sines. We don't get anything less than -1 for sines. So it's got to be in between. If we're trying to make this whole equation, this whole function as big as possible, well, the biggest we can get is when that's a 1. Okay, when you're just controlling the sign. So that's what this problem has become, is we want to figure out what value is going to, what angle is going to give us the best distance. Well, it's when literally sine of 2 theta equals 1. Well, think, I know when sine equals 1, it's when this is 90 degrees or pi over 2. That's the best sine will be. So the answer pretty much is, let that equal 90 degrees, and theta is going to give you a 45 degree as our answer. Which kind of makes sense, because if you look at the examples I was telling you with that cannon, if you have a no angle, you're going to shoot the cannon and it's just going to fall right to the ground immediately. As you rise it, it goes distances, but if you rise it too high, 90 degrees, it's going to go straight up and down in the air and you get nothing. Now keep in mind, sine, when that's 90 degrees is our best angle, best way to do this, but it's a 2 theta that we are solving for it, and that's why we get a 45 degree. So it kind of makes sense, if you want to get the best angle, best distance, you shoot it at a 45 degree angle. Okay? This is pretty much the same in any kind of a sport. Like I said, any kind of an object you're throwing or launching, 45 degrees is the magical angle. Now you may find though that you may do better at 42 degrees or 41 degrees because there's another factor, a little bit of air resistance comes into play. So in real life applications, it's going to be a little bit smaller, but as you take a physics class, you apply the calculus stuff to the physics and you'll find the exact value that, you know, in a vacuum, 45 degrees is the winner. But when there is air resistance, it's probably 41, 42 degrees, something like that. Okay, but based on this equation, here's our answer. Any questions on that part? Anything I've written here that I'm erasing or what I'm talking about? Okay. I know it's your Friday, so I'm not going to try to keep you all day if possible here. So we get the 45 degrees, maximum range. And now the next part is we're just going to do a couple more formulas. And I'll be honest with you, I never tell my class to memorize these. These things come up once in a while. They're not worth the stress to memorize. If I was to give this on a test in real life, in a classroom setting, I would give these formulas and just see if my students can apply them. Okay? So essentially what they are is as they're named, they're half-angle formulas. Right here, I don't know why there's 2. Oh, okay, we'll get to that in a second. These formulas right here, they're just another way to break it down. If you look at it, they're the same formula a couple slides ago, where we had, remember, I'll go with the cosine because we've been doing that. Remember, cosine square of theta equals 1 plus cosine of 2 theta over 2. And the main gist is when you convert this over, this doubles. Okay? Well, guess what? It applies for every angle. If this was the original angle, it's the same formula. We double it there, and that's exactly what happened. So whether you call it going that way and taking a half or going this way and doubling, it's the same thing for these formulas. It's the same formula you had already. But there's a reason they're doing this, okay? And it's where this next slide is. We want to solve for, go back. Okay, see these two right here, the ones that these are based on the ones we already had. We're going to square root both sides. So when you square root this side and you square this side, that square cancels with the square root. And then, of course, you need to have your little plus or minus in front of the other side. So that's how they went to this, where you get sine of alpha over 2 equals plus or minus the square root of 1 minus cosine alpha over 2. So, like the name, they're half-angle formulas. We had earlier double-angle formulas. It's the same thing. If you get an angle that's half of something, you can rewrite it with the thing that's on the right. Okay? But you need to make sure, have that plus or minus. Depends on where, and you see at the bottom, they do give you a little hint. You pick the one depending on which quadrant you're in. If you're dealing with a sine, you know what quadrant sine is positive, and you know where it's negative. So that's the extra bit. We've kind of already done that when we solve things. So use a half-angle formula to find the exact value of 75 degrees. As you recall, we do not have a memorization of sine of 75. That's not one of the angles I gave you. But we do have a 150. So we can get this by thinking, well, 75 is the same as 150 over 2. So my alpha is going to be 150. All right, so go back and look at this. We're looking for cosine of 75 degrees. That's exactly the same, and don't be afraid to write this, as 150 degrees over 2. We do that so that it fits the formula. Okay, that one right there. When you have some angle over 2, you can use the half-angle formula to basically say, okay, I got 150 over 2. When I replace it on the right side, I'm going to use the 150. Go back one more time. Look at that formula. Okay, if this is my 150, that becomes 150. So that's why you get what you're seeing two slides from now. Okay, so based on the formula, you put in that 150. And remember, oh, how do you know it's a plus or minus? Let's go to that too. They did not. They kind of told you. Well, think about this. Here's the original problem, not this one, this. Where is 75 degrees? It's right here. And this is where you got to say, oh yeah, cosine is positive. I know that. I don't know what the answer is to cosine of 75 degrees, but I know it's in the first quadrant, and I know all cosines in the first quadrant are positive. That's why I chose the positive of that plus minus formula. So always write the plus or minus, and then once you conclude where it is, now you don't have to write that plus minus for that problem. So we think of, well, what's the cosine of 150? That's supposed to be something you know. That's your root 3 over 2, negative root 3 over 2, sorry. And then we got to do a little algebra, and you're going to see we have a root inside of a root. Not fun, but it does work. And then we simplified it here. And if you're not sure how they did that step, just think, let's multiply top and bottom by 2. That's how you get the 4. That's how these cancel. And that's how that became a 2. And this is as far as you need to go. And the last part was they took the square root of 4. That's why there's just a plain 2 on the bottom. Okay, so that is your exact answer. You know, don't think, oh, I got to do something more with this root in a root. You don't. The one thing you don't do is don't go get a decimal. Okay, you have the exact value right here. And you're going to get this as you get more and more questions about angles that are not in our sheet. You're going to get some weird looking answers, but that's how it's going to go. But at least you're going to be able to get a precision answer. That's the nice thing. Okay, so now I'm going to get formula after formula. Remember that one time that if you have a negative angle, you can pull it out front for sine, only for sine. And then, excuse me, you can do this. So that's what we're looking for. The question was find the sine of negative 75 degrees. Well, I can call that the same as negative sine of 150 over 2. then you plug it into the formula, and you're going to see it's the same thing, but a negative out in front. Okay, that's all it was. All right? Now, some more of the ones I like here. You get cosine of alpha equals negative 2/3, and they tell you that alpha has got to be between pi and 3 pi over 2. That means my alpha is somewhere in that third quadrant. So remember my right triangle approach? I know it's going to be down there. I know that we have this right here. We have a, cosine is negative 2/3. So there's a negative 2, there's a 3. And I can do the Pythagorean to get that y. All right? Then, once I get that y, let's just do it real quick. Negative 2 squared plus y squared equals 3 squared. Y squared equals 9 minus 4, which is 5. We get a plus or minus root 5. Well, we're in the third quadrant, so that y is going down. We get that. Okay, so what that tells me is, remember, once you solve a triangle for any angle, like this case alpha, you can go find any of the 6 trig functions for that. Okay, does that help? Maybe, maybe not. But what we're looking for is, this is what they want us to find. They want us to find sine of alpha over 2. Well, I know everything I know about alpha. I don't know anything about alpha over 2. However, go back. Remember our formula? I'm trying to show you that without erasing what I just wrote. Okay, remember? Sine of alpha over 2, we can solve it if we know alpha, but we need cosine of alpha. That's why I built that triangle. So the triangle allows me to find anything, oops, sorry, not this one. Anything about any alpha, and the formula required me to know cosine. Now, where are we at here? Look at the formula. I'll write this again. The formula should be a plus or minus. Now, the step they didn't show before was, think about this way. My alpha, this angle right here, is anywhere between 180 and 270 degrees. Okay? What we care about, though, is alpha over 2. So we need half of that. Well, the biggest alpha over 2 can be is half of this, 135. The lowest it could be is half of that, which is 90. It's got to be somewhere around here. My alpha over 2 has got to be somewhere in there. What I'm doing this for is to show you that it's the second quadrant, and when it's in the second quadrant, sine is always positive. So that's why you don't see the plus or minus. They did mention that in the slide before, but they didn't say why, or they didn't really make it as clear as I would want it to be. Okay? So all that idea of figuring out what the quadrant is, that's just so you know which one of these to pick, which plus or minus to pick. Okay, but what matters now is I got to get cosine of alpha. Lucky for me, I've solved my triangle, and I know from that triangle right there that cosine of alpha is negative 2 over 3. I'm trying to remember. Oh, they gave it to us before. Yeah. In the very beginning, they gave us a cosine alpha. I didn't need the triangle. So I just plug in the negative 2/3, get a common denominator, divide it all out, and I should get square root of 5/6. Okay, now I'm not erasing the other stuff, I'm sorry, for a second, just so that I can, because I know what I'm going to do in the next problem. But again, without stuff all over it. Cosine of alpha is negative 2/3. 1 plus 2/3 is 5/3. Divide that by 2, we get square root of 5/6. This should work when you plug it in, or you can rationalize it and get this. And they did this wrong. I'm sorry. Don't look at this. It's supposed to be the 5. It's supposed to be all of that in there. It should be the 5 and the 6 should be inside. It should be the root 30 over 6. That's why I say just go with this one right down there. Okay? So watch that if you download the slides, like Kayla, whoever else was thinking of looking at the slides. That wasn't exactly the way it's supposed to be at the end there. Okay, let's move on, though. We'll look at the next example they gave us. Okay, now we want to get the cosine of alpha over 2. That's the question they're looking for right here. So same thing as before. Remember, cosine of alpha over 2, that's the thing we're trying to find here. And remember, since alpha is in the third quadrant, alpha over 2 has got to be somewhere around there. It's got to be in the second quadrant, but this time cosine is negative. Whatever I know, I just know my answer is going to be negative. So that's why when I use this formula, the one that had the plus or minus on there, that's why I'm picking the negative. All right, because I know it has to be in the second quadrant where all cosines are negative values. So I know the cosine right here. Cosine of theta equals negative 2/3. I'm going to do the same thing and just replace this. And we get a negative square root of 1/6. And again, that one's correct when you rationalize it. So it's about using the formula. The two extra things you have to do. Determine if it's the plus or minus. And don't just pick the positive every time because you want to. You have to identify what quadrant you're in. And the key is, it's not where alpha is, it's where that one is. This quadrant is going to tell you if you pick the plus or the minus. Okay, not the alpha. So that's one of the awkward parts is a lot of people start looking at the alpha. It's not the alpha that's going to tell us. It's half of the alpha that we're looking for. Where is that one? The actual problem we're trying to find. Okay, so now in this one, we need to find tangent of alpha over 2. And we're in the same question because tangent is going to be somewhere between 90 and 135 degrees. And that means second quadrant. That means tangent has to be negative. So on the formula for the half angle of tangent, we pick the negative of the plus minus. And again, we got to know the two cosines. We know these, both negative 2/3, and it's actually an easier problem to work out. Tangent looks uglier, but it actually is a little bit nicer a lot of times. Okay, so what wasn't necessary? You didn't have to build the triangle like I did. Sometimes you would. So if I go back and I look at this original problem they gave us. Oh, too far. Right here, okay. They gave us the cosine of alpha. They told us where alpha is. On all three of these problems, we had to get the alpha over 2. So step one, always figure out the problems you're finding. What is the quadrant of this angle? In this case, alpha over 2. Now, I used these two bits of information to make my triangle. It didn't need to happen because all of your formulas, go back a few more slides, every formula is calling upon cosine of alpha. So that's really all you have to get is get cosine of alpha. Now, if they happen to give us this problem, and in the beginning, instead of giving us cosine of alpha, let's say they told me, no, we're not going to give you cosine of alpha, but we gave you sine of alpha. Well, then we're going to have problems when we use our formulas. That's the case where you'd have to draw the triangle and plug in the negative 2/3, get whatever this is, what do we say is root 5. Now you can get cosine. So depending on what they give you, if they give you the cosine of the alpha, then you're good to go. But if they give you anything else, you have to spend an extra step to get the cosine of alpha. Okay? And then it's just a matter of plugging in the formula. And you see why I don't need people to memorize these formulas. It's more important of, can you do the steps leading up to it? Can you plug it in correctly and get the answer? Okay, so moving forward from there, we did the sine, we did the tangent, and that's pretty much it for this set of slides. Let me do again your favorite part. Let's get to the assignments here. See where we're at in the homework. So again, we have done half of this assignment, the 7.5 stuff. Let's look at what the rest of these questions were. So let's look at number 35 and just see where we are. Clear everything out for you. Okay, decide whether the following statement is true or false. Okay, so when we're doing these, remember, we're trying to figure out, we don't have to necessarily prove the identity, but we just want to see, is it a true statement? So I'll cheat a little bit and give you this right here. We're looking for tangent of 2 theta. When you see that, oh, wrong slide, sorry. Go back, trying to pull up the one we just had today. Okay, remember one of our first formulas we did earlier. Now we had only these for the double angles. They give us a tangent of 2 theta. Okay, so I don't really have much on that one. Do we have a formula? Well, go through. There's not an exact one except right down here. Remember, oh, sorry. We proved this one. And then, sorry, let me make that a little bigger. And how we proved it, remember, was we used the sum formula before. We just did a theta plus theta, got all this stuff right here. So this is what we're going to use. And basically, we just have to decide if it's true or false. We already had this. Now, let's just say this is the test and you didn't look at this PowerPoint slide. Remember, the process is, if I'm trying to get what tangent of 2 theta is, I break this down with theta plus theta, and then I do all that work that we learned in the last section, and that's what this example was. Got a tangent plus a tangent. On the bottom, you get a 1 minus tangent times tangent. That becomes a tan square. That becomes a 2 tangent, and it wasn't much to it. That's all we had, and say, yeah, true or false, and that's it. Okay? And they even prove it right here, just in case you didn't look at the PowerPoint slide. So nothing earth-shattering on that first one, but we'll get to number 39. You'll see something a little more up our alley. Now, as these problems get bigger, this is going to apply to everything else in the rest of our summer semester here. You got to make sure you really read the directions. You've even seen me sometimes where I sort of coast through it quickly because I'm trying to get it done and get more problems for you. And by not reading the instructions, sometimes I miss something important or I do the wrong thing that they're asking for. So they tell you to use the half angle formulas to find the exact value of cosine of 165 degrees. Well, remember, this is the exact same thing as cosine of 330 over 2. Okay with that? Now we need to come up with what's the formula. That's our half angle. Now we've had this before. We've done a lot in the last couple minutes here. But remember that. The ones with the plus minuses. Oh, I'm sorry. Much further along here. Right here. Make sure it looks just like what you're solving for. Yep, it looks like it's this second one right here. All right, to help you, not to memorize it, but it will help you to memorize it. Just to help you plug things in correctly, I'm going to say write that formula down. Don't just look at the formula on your sheet, or in this case, my PowerPoint slide, and start plugging in. I'm going to tell you, write it down, and now you're in a better position. Okay? So keep in mind, this whole thing is alpha over 2. This thing is alpha over 2. Therefore, my alpha equals the 330. So when I'm using this problem right here, I have to first figure out what the plus or minus is, but I'm just going to jump ahead and say it's 330 that I'm plugging into this formula. Okay, now I got to figure out where, if I'm doing the plus or minus. To get the plus or minus, remember, it's this. Where's 165 degrees? Somewhere right around there. And since we're talking about cosine, I know cosine is negative in that spot. That's why the reason, not just guessing, that's how I know that my problem is going to be negative. It's going to be negative all of this. Okay? Identify that negative. Yet I am sorry, my alphas do look a little funny like the 2s. So just keep in mind, you're never going to see a 2 just like that inside there. I generally don't like to use alphas. I like to use thetas or something else so I don't make that mistake. But if I'm writing something, you guys, and you're wondering, is that a 2 or is that an alpha? Like right up here, I can understand you. They do look the same. The top is an alpha, the bottom is a 2. So that's just my bad handwriting. I'll try to fix that. But don't be afraid to ask me, Jason, or anybody else, if you're not sure what I have there. Okay? So now, figuring out where we are here, we know it's negative. We have to figure out, well, what's the cosine of 330 degrees? All right, you guys have that memorized, right? Cosine of 330, hopefully you got this root 3 over 2, and it's positive. Now, some of you may be wondering, a minute ago, we just determined that it's going to be a negative cosine. Correct. The thing we're looking for, the 165 degrees, this is in the second quadrant. That's going to be negative. That's what matters. Right now in my formula, I'm using cosine of 330. That's a positive number, but that's just part. It's a step in my formula. So that's what I'm trying to figure out. So we are going to get, maybe I'll do that thing where I did earlier. Let's multiply everybody by 2. That'll make the little fraction cancel. So I'm left with a negative root of 2 plus root 3 over 4. And then my last step is I maybe just take the square root of that bottom part, and it's just a plain 2. So you notice one step, the 4 is under the square root, and that last one, it's gone because I took the square root of it. So this is as far as you need to go. We have negative, fraction button, the square root of 2 plus the square root of 3 all over 2. And before I check my answer, I'm going to try one thing and see if this is going to work or not. Okay, it's, I won't call it a cheat. It's a smart way to check your work. All right, let's try this. I'm in degree mode. Let's hit the cosine of that. When we get this negative 0.965. Okay, just need a few decimals. You know if it's right. Now, the exact answer I got was down here. Let's see if this works. So we're going to do the square root of 3 plus the number 2. This 3.73 is all that's inside my root down here. I'm going to take the square root of that. I'm going to divide that by 2, and I'm going to make it a negative. And what do you know? We get the negative 0.9659. That's a way you can use, and I'm going to tell you, yes, use that on your quiz or your homework just to kind of confirm you have the right answer. A calculator is not going to give you this precise number down here on the bottom right. But if you get the precise root number fraction, you can get a decimal value, take the original problem, get that decimal value, and see if they match up. That'll kind of be your way of knowing that you're on the right track. Or if you got it wrong, like I said, it's not going to tell you what the right answer is, but it will tell you, do your problem again or check your work. All right, so let's look at number 43. Okay, use the figure to evaluate the following function. Now, let's make this a little larger. They want us to find h of 2 theta. Okay, so what they give us is, they give us this formula, they give you this circle. It's not a unit circle, by the way. If it was a unit circle, it would have that equation. So it's a circle, still centered at 0, 0, but it's got a radius of 5. Okay, 5 is how far out we are. And that helps because you see this triangle right here? I know that number is 5 of that little triangle. So I'm just going to take this triangle right here. We have this point A comma 1. Since the radius is 5 of that, oh, I'm sorry, it's not 5. It's the square root of 5. My apologies. The radius is always the square root of that number right there. This number. So all of these are root 5s. Important part. We would have gotten it wrong if we didn't do that. So the radius is root 5. When I have the point A1, that means this is A, the height of that triangle is going to be 1. That's where that point is. So what I have to do next is figure out, well, what is going to be the actual, the value of the x right here. So I do my Pythagorean theorem. We get a squared plus 1 equals 5, a squared equals 4, so a equals plus or minus 2. And remember, where the triangle is, that a value is a negative, so this right here is a negative 2, that bottom side. Now, that's all from the picture. So I'm going to get rid of the picture now that we've basically taken everything we need out of there. And let's focus on what they need us to find. They want us to find h of 2 theta, which means find, the tangent of 2 theta. So we've done all this preliminary work. Now we get to that formula. Don't worry, if you don't have this formula memorized, as I've said many times. You have the reference right here. Okay, now it's not the half angle. We're back up here somewhere. We're at our double angle, right down there. Oop. That one right there. Okay? That's the formula we need for the tangent of 2 theta. Because remember, everything we know is based on alpha. This little triangle that I just did, this involves, I'm sorry, not alpha, this involves regular theta. Regular theta, we don't know anything about 2 times it. Okay? So we have to go get our formula and say, all right, let's look at this. We have this tangent of 2 theta, all this right here, this is going to be equal to 2 tangent of theta all over 1 minus tan square of theta. Now notice this is not one of the double angles are not the ones that have the plus or minuses. So we don't have to make that determination of where we are. And in fact, you don't know which quadrant you're in. You could be in the 4th quadrant. You could actually be in the 5th or the back to the 1st quadrant, depending on what they were. So good news is there's no plus minus. We do not have to make the determination of where the 2 theta is. We just plug in what we have. So remember, based on my triangle, I know that the tangent of theta from way down here, tangent of theta, regular theta, is going to be 1 over negative 2, or negative 1/2. All right? Remember, y over x, we have that. So I'm going to replace each of these in my formula with that right there. So we get 2 times negative 1/2. We get 1 minus negative 1/2 squared. And then just keep cleaning this up a little bit. Negative 1 on top, 1 minus a 4th. Negative 1 over 3/4. And in the end, negative 4/3. Hopefully, that's our answer right there. And you see how much algebra we did right there. And that's it for number, was that 43? All right, questions on 43 from anyone before I delete all this? Okay, let's look at 47. All right, establish this identity. All right, so we have the cotangent of 2 theta. And we want to get it equal to cotangent of theta minus 1/2 secant theta cosecant theta. All right, so this is going to be an interesting one. We'll go through it. Now remember, when we're doing this, I've always said when you establish the identity, the idea is answer the left side or take one side, the more complicated side, and try to make it the other one. Now this one looks more complicated. So I could make the argument, let's do this one and see if we get to here. This one's more complicated in the fact of that it has a 2 theta. So they're both, there's good reason to use either. Now the good news is it doesn't matter. And it may be that you go through it and you're like, well, you know what? I wasn't getting anywhere with this one. Maybe I'll start with this one. Okay, and that's going to be the process sometimes. So let me start with the left, and if we have time, I can go to the right as well. I'm trying to think here. How do I make that happen? Okay, this is a cotangent of 2 theta. If I look at my identities for my little cheat sheet, I don't have that. I've got tangent of 2 theta. I've got sine and cosine. I don't really have that, but I do remember something about this. Remember, cotangent is the same as 1 over tangent of 2 theta. Therefore, I can replace it with all this stuff down here. And I didn't need this step. Basically, what it is I'm just going to take the reciprocal of that. Now, what's good about what I've done so far, I've gotten it from 2 theta down to theta, and that's what everything here on the right is. These all have the 2 theta. So now I just got to try to see if I can make what I have here somehow equal to what's over there. All right. So let's move this one up. And if I'm not seeing anywhere to go, like I don't see any immediate identities, I'm going to go back to our favorite old approach of let's make everything sines and cosines. So tangent square theta is sine square over cosine square. And on the bottom, we have 2 sine theta over cosine theta. Okay, now I'm still not seeing that right here, but let's just kind of look at what's going to happen. Let's try this. Let's multiply everybody by cosine square. Now, why I'm doing this is it's going to distribute to here and to here, but when it distributes to this one, it's going to cancel it off. Down here, it's going to cancel one of them. And a lot of times, as I said before, when you're doing these proofs, you may have to just try a couple things out just to see what happens. And sometimes things work, sometimes they don't work. Now, I see a couple good things here. Some things that I like, some things I kind of worry about, but you'll see it's going to get better in a second. I like that I've gotten rid of the big fractions. So instead of a complex fraction, I have just one regular fraction. Jason, to answer your question, when I say it's a measure of complexity, like how hard these problems are, there is a system in the problems I assign you guys where some are easy, some are medium, some are difficult. There's a number of factors. How long does it take? How many steps there are? How many formulas you have to use? This one is more of a complex one because it's going to take a couple more steps. All right, so what I'm going to do next is, remember, there's one term down here. Oh, I'm sorry. Answer that question, Jason. Which side to start? It's kind of like that too. I see a bunch of terms on the right. That might be a complex side. I'll start with that one. On the left, I don't like the 2 theta. Maybe I want to get rid of that first. Maybe you might want to get rid of the 2 theta and then work on the right side. That's kind of an option. But at some point, you have to convert from either thetas to 2 thetas or 2 thetas to theta to make the sides equal. And I'll tell you guys, to be honest, there's never a wrong side to pick to work on an identity. Some are just a little bit longer, a little more intensive than others, some methods, but both ways should work no matter which side you pick. So what I was saying was when we get down to one term on the bottom, remember, even though that has a number 2 and it has a sine, it has a cosine, they're all multiplied together. So it's one term. I can split this fraction as both of them being over sine cosine. So I write the cosine square over 2 sine cosine and the minus sine square over 2 sine cosine. And that is going to make one of these cosines cancel, and it's going to make one of these sines cancel if I've got everything that I'm supposed to. So now I end up having a cosine theta over a sine theta, 2 sine theta, and a sine theta over a 2 cosine theta. All right, now I'm getting closer to what I'm supposed to have in this problem. Remember, my goal is all of this up here. All right, that's what I'm trying to make this all look like. Make sure I wrote that down right. Yeah, cotangent theta minus a half secant cosecant, okay? That's what I'm trying to get here. So I'm getting there. If you look at what I have the cotangent. This cosine over sine, that's essentially a cotangent. That's good. Here, I kind of am close, but I'm not quite there yet. Got a couple more things I need to do. So see what else we can do. See what else we can make happen. But let's look at where we are. This is a cotangent theta over 2. This is a tangent over 2. So not quite there. Like I said, if I'm doing a checklist, I've got this, but I've got some extra 2 in the bottom. Got to deal with that somehow, okay? Then I've got the other part. The tangent is not even close to what that is. And I'm not going to say I recommend this every time, but sometimes you might want to rewrite and see what you have here, okay? So here's what I'm going to do next for the benefit of time. We're going to get there eventually, but if you get stuck, and that's why this is a good example. Let's say I'm looking at that, and you're looking at this, and you're like, I don't know where to go next because I'm not quite there. This is where I'm going to go back. Because remember, these identities, they just want you to prove or show which option is the best one. Okay, so let me try to write this, or let me try to get this in our screen a little bit. They have 4 choices. Like I said, I'm trying not to lose what I have. Okay, so notice what they did. They took the cotangent 2 theta like I did. They rewrote it as cosine 2 theta over sine 2 theta for each of those. Okay, different approach than I took. Eventually mine would have gotten there. And this is where I'm going to tell you, don't be afraid to look ahead and say, oh, look at this. I went a different way. So mine is not going to match theirs. So I'm not going to say it's no good, but I'm going to erase it just because I want to write what we're supposed to do here. This, like I said, if I kept going, I would then take this tangent and I would rework this a little bit. Eventually, I'm going to get up to here. And I'm going to get something else that would make this 2 cancel. Okay, what I would have gotten was I would have somehow out of here, another cotangent of theta over 2 would have come about. And when you combine it this one, it would have been a single cotangent. And then I would have been left with all this stuff. Okay, but like I said, to fit with what they're doing, let's go back one more step. Kind of follow where they're going. And this is, like I said, for this class, this is the nice thing is you kind of get this, I don't want to call it a cheat, but you get this option right here. So you look at that, all 4 of the options had that. I think they did. Okay. They're all cotangents. They all were cosine of 2 theta over sine 2 theta. So this part's consistent. Nothing to worry about there. And that's where we are. Now is the next line where they all get here to here. And what do they become? Okay, so you got to think of what's the formula for them. All right, what's the formula for each of these? Well, sine 2 theta, we already know, is 2 sine theta cosine theta. That's a given. There's only one option for sine 2 theta. Remember that? So this one has it, this one has it, this one has it, this one has it. Okay, we didn't get anywhere. But now you look at the different options for the cosine and see what we can eliminate. Now, if you forgot what they were, I'll help you out one more time. Show you them. They're our very first ones the other day. Okay? Look at all these. We did the sine. Cosine, it's cosine squared minus sine squared. Well, this third choice has that, so that's good. Or it could be 1 minus 2 sine squared. None of them have that. Or it could be 2 cosine squared minus 1. This one has it. This one has a plus 1. So at least I can say, nope, D's gone. Okay? So we're proving it kind of weird here in this one because now they went 3 different directions to try to get to our end goal. And sometimes it's going to be a case of, well, maybe you just do the teacher role and let's just grade this and see what we can get. Okay? See if you can figure out what's going on. So let's just follow the train of thought on A, B, and C. We've already eliminated D, so no longer consider D. Let's just follow A and see if we can get the logic. And if anything, what you're looking for is, my tip to you, you're looking for an error. And you find an error, you mark it wrong, and that's out. So what did they do right here on part A? They rewrote this as 2 fractions, like I did earlier in my other example. 1 over the denominator minus 2 sine square over the denominator. That works pretty good. Okay? Then, all of a sudden you have a cotangent. Cannot go from here to a cotangent. This is what I'll see on a test where people be like, they just, oh, I want to write the answer right there. So that doesn't look very good. All right? But we'll come back because maybe there's another step in between that we did not see. Because also I see these 2's should have canceled right here, but all of a sudden they just went to this. So maybe there's missing steps, which isn't good, or maybe it's wrong. Okay, we'll come back. The second one, they did the same thing. They rewrote this as two fractions. 2 cosine theta over 2 sine cosine minus 1 over that. And on this case, you see the cosines cancel, the 2's cancel, and we clearly have a cosine over sine, which gives me a cotangent. And then over here, the negative 1/2 is still there, and they brought the sine and cosine up to make secant cosecant. So that one looks pretty good. Okay, so right now that's my leading horse. I see no errors with number 2. It looks like they proved it right. Part C, again, they split this into 2, but notice when they split it, well, I guess they didn't show that step here, but they split it, and this is cosine square over this, so one of the cosines canceled. That's why we're left with cosine over 2 sine and sine over 2 cosine. And then they do get a cotangent, but there's that 2 lingering right there, so that doesn't look right. And then over here, there's the 1/2. They brought the cosine up to make a secant, but the cosecant should not have appeared, so that one's wrong. So based on all of that, I'm looking at that and say, well, there's no choice. This has got to be a B, and there's our solution. Okay, if I was to keep going with this, like I said, it's if we were not looking at any of this and we were just trying to prove it, you do have to, right at this point on my writing, you have to make a decision which of those formulas are you going to use for cosine. You've got 3 of them, okay? It's hard to tell. If I'm looking at this right off the bat, I don't know which one's best. I generally like one of the second one or the third one right here, just because it's only one trig function versus 2, and it's got the trig function in front, not a negative trig function. But it's one of these where you just have to kind of mess around a little bit and see what you get. And if any time you're in an identity or proof and it doesn't work, you feel it's not going anywhere, pause, go back a couple steps, see if there's another road you could have taken. It's just like if you're out hiking and you go off path a little bit, you're going to walk a few bits, and then if you realize, hey, this is not good, you back up. You don't necessarily go back to the start, but you go back far enough where you see, oh, here's another opening. Let's see what we can get here. And then you go through it. Okay? So that was our number, what was that, 47. Let's look at a couple more here. Let's look at 51. So same thing, we have to establish this identity. Now on this one, let's do that same approach. I won't write everything out, but here you see they took a few different approaches. So to make a 3 theta, one option is you can do a 4 theta minus theta. One option is a 2 theta plus a theta, or that 4 theta minus theta. And notice there's only 3 choices here. That's good for us. Let's go line by line. Okay, like I said, this is a little bit longer of a process, but I like it because it's going to make you guys be the teachers and you can kind of see what's going on. All right, so what we have to look at here is what's the formula for when we're subtracting 2? That's not in here. Remember, we didn't do that here. That's the stuff that's in the 7.5, the one that I had open a second ago that I closed, the one we just did. So remember the formula for, what did we say? Are we on tangent? Yeah. Tangent when we're adding 2 up. We've done this before. In fact, it was in that last slide. I could have used it, but this is what we have. Adding 2 tangents or subtracting, because we have both versions here on this one. Sorry. So in this first case, we're doing the subtraction tangent. So let's just check the work. The formula should be tangent minus tangent. Tangent of the first minus the second. Well, right here, I'm looking at this and going, where did you get a 2 theta? Why is it a theta? This already is wrong, okay? It's supposed to be, on a subtraction formula, it's supposed to be tangent of the first minus tangent of the second. We don't have any of that. So A is not looking good for me. I'm going to get rid of that. Let's go back to B. Let's see what B looks like. We get a tan of theta, 2 things, 2 theta plus theta, 2 theta plus theta, yeah. So it's a tan of the first plus a tan of the second. That looks good. 1 minus the tangents multiplied together. That looks good. Okay. Now we go to the second step. And in case you're forgetting, well, where'd they get that from? Let's look at our, we gotta pull it up. The one from today. Okay. Remember our tangent of 2 theta, what they're replacing here is tan of 2 theta. That one that we, quote, established. So we need to replace this tangent right here and this tangent of 2 theta with that. So let's see if they did that correctly. We get a 2 tan theta over a 1 minus tan square theta. That looks good. We did a 2 tan theta, 1 minus tan square theta. That looks good. Okay? So far in part B, we're good up through here. Check mark. We're happy with that one. Now, we have to figure out where in the world did they get all this from? So there's a leap of faith coming here. There's a part that they didn't explain. So let me see if I can try to draw this out for you. What we're going to do is we're going to multiply everything by 1 minus tan squared. And same thing down here. Everything is going to get multiplied by 1 minus tan squared theta. Now the reason is I want to get rid of this and get rid of this. So when I multiply that parenthesis to the first term, it'll do that, but I also have to multiply it to tangent right here. Okay? So just on the top, if you look at what we get, it cancels and we're left with a 2 tangent theta on top. And then for this part, it's tangent times each piece. So it's a tangent times the 1 minus a tangent times a tangent square. It's a tan 3. So the top should turn out to be 3 tangent theta minus tangent cube theta. And that's what they had right there. Okay? So again, I'm trying to fill in the blanks here on what they did. Now we do the same thing on the bottom. When we move it to the 1, that's going to give me 1 minus tangent square theta. And when I do it over to this one, it's going to cancel. So all we're left with is the 2 tan times a tan. So that's going to be a 2, minus 2 tan square theta. Well, those combine to be 1 minus tan to the third theta. 10 to the square, not third, tan square theta. And now that's my denominator, that's my numerator, and it does match that one right there. So that's how I know it's going to be B. Let me kill this off, and before I enter it, I still want to give part C some consideration. Okay, so back to our subtraction, we should have tan of the first minus tan of the second. We have an addition. Right there, I'm already going to call foul. No good. Now I know B is my answer. So they made it where there's only 3 choices, and if you look at it, this is a complicated problem. This proof is going to take a while if you did it all on your own without any of this help, without looking at the multiple choice. But they did it at least in such a way, even though it's a hard problem, the bad choices failed pretty early, and the good choice made it all the way through to the end. So it's kind of like you can see somebody pull away from this race a lot faster. So you're not going to get a ton of these. I threw a couple of them on there just to kind of keep you honest, to make sure you can, to challenge you a little bit, to make sure you can do these difficult ones. Let's look at this one here. Find the exact value of the expression. Okay, so we didn't do one like this yet, so I'll show you where we're at. We have sine of 2 inverse cosine of negative 5/13. Okay, so now here's where it gets interesting. That inverse function, like always, is going to be a theta. Not the whole thing. Not all of this is going to be theta. It's just the inverse trig function. We're going to say inverse cosine, inverse cosine of negative 5/13 is going to be my theta. Therefore, the cosine of theta is negative 5/13. So what I'm going to do next is I'm going to make our triangle for our theta. All right. Inverse cosine is going to either be in the first or the second quadrant. Because it's negative, I know, let's make that a straight line. I know my theta has to be in the second quadrant. And sure enough, that means it's a negative 5 here and it's a 13 here when I do the Pythagorean theorem. Okay? If you knew there was such thing as a 5, 12, 13 triangle, you would have the answer. If you do the Pythagorean theorem, just to save you trouble, you are going to get a 12. And because, again, it's in the second quadrant, the y value has to be positive. So that's why it's the plus 12. So now remember what this triangle means is I know everything about theta. I know sine, cosine, tangent, everything about theta from that triangle right there. Now, it doesn't help us all the way because what we have to do is we are looking for sine of 2 theta. Remember that 2. That 2 is part of this. So I got to go figure out sine 2 theta. How do I do that? I use one of my formulas from today, which is sine 2 theta is 2 times sine and cosine of theta. So now I go to my triangle. The sine of theta is 12/13. The cosine of theta is negative 5/13. We multiply all these together and we get, I think, a negative 120 over 169. And there's our answer. Okay? Once you build that triangle, it's not that bad because you build the triangle and then you just have to go and figure out what the formula is, and it's just a simple replacement. The big thing is, what we've been doing before is this whole thing is theta, and then we would just go find sine of theta. It's not just giving you the 12/13. It's sine of 2 theta, which means go find the right formula. If this was cosine of 2 theta, we'd have to go and use one of those 3 formulas, and then again, use this triangle to fill in the blanks. So hopefully, I think I got everything right on that one, and we're good. So that's it for number 55. Questions on that one? Okay. Let's see, was there a 59? I think there is, but I might have taken it. No, I think I left it in there. Okay. Find the value of the number c. Now, this is an interesting one. We're trying to solve for c, but we got to get this in terms of the cosine, the sine, and the idea is that whatever c you pick, this must be a true statement for every single c. Okay, so I'll remind you. Let's see how far we can go without doing this. But remember, if you get to one of these awkward ones, you got this option down here to get more help. If you want to view an example, you can view an example of it. Notice it's not the same numbers, but it can give you kind of a hint of where to go. Okay, it can point you in the right direction. So here's what I want to do. I want to try to get everything in the same terms. It's like an identity, but it's not exactly the same. I'm going to take the full space probably to work this one. We have a negative 1/4 sine square of x plus c equals 1/8 cosine of 2x. Okay, so it's like an identity, but there's that c in there. We're really trying to find the value of c. Let's do this so that we don't have to deal with the 2 different angles of x and 2x. Because remember, when you get a cosine x, 2x, and a sine of x, you can't put them together. You can't use an identity and make them a cotangent or a tangent. They're independent letters. So let's try to get everything in terms of sine and cosine. All right? So if you remember your formulas, let's try, where are we at here? Our double angle, the stuff from the other day. Oh, sorry, not that one. The one earlier today. Okay, now remember, I have my 3 options. Now look at the choices. I can replace this whole right side, the 1/8, but the cosine 2x, I can replace with cosine square minus sine square, 1 minus 2 sine square x, or 2 cosine square x. This is where you look at the rest of the problem. Hey, I've already got a sine square. I don't want to bring another cosine square. Let's leave this all as a sine square. Let's pick this one right here. Now, it doesn't mean it wouldn't work with the other ones. What it means is you'd have to do a few more steps and you'd ultimately end up in the same place we're going to be at right now. Okay, so now I want you to put on your algebra hats. Let's just simplify the right side. That means I get a 1/8 x and a minus 1/4 sine square x. 1/8 times 2 gives me the 1/4. Now, if this is proving an identity, I would tell you can't jump things from left to right, but that's not an identity. We're trying to solve for c, so why can't I bring this over? This right here, I'm bringing over to the right side, which makes it a positive 1/4 sine square x. And hopefully you guys are starting to see this is not as bad of a problem as it might have appeared. This and this cancel right off because they're identical. They're both sine square x. And now I get c as an eighth. That's it. That's all you need to do on this problem. I lost my browser. There it is. Hopefully this 1/8 is all they wanted. And we get our well done. Okay, so that's it for this particular homework. You should be good to go for all of these. For the last few minutes here, let me just go through and let's talk about our quiz. Different quizzes here. So we kind of talked about the quiz the other day for the one that's due tonight. So let's look at quiz 6, which is due on Monday. Oh, sorry, that's homework. Quiz 6, there it is. Okay, remember, due 3 days from now. And remember, once you click that continue, you're in. So 2 tries. So try one as soon as possible and then give yourself some time to go in, figure out the rest if you need to, modify this. So I'll go through these a little bit for a few minutes just to give you guys a quick preview of how this is. If you're watching the recording, I may not show you all of it here. This is a little reward for coming to class, but I'll be nice and I'll just show this to everybody today. So on this one, I'll walk you through what you need to do here. In both cases, if you look at sine, cosine, they're both the sum and angle formulas. Okay, so remember, sum and angle formulas. The tangents are easy. They just require you have to know the tangent of each. So when I have a plus b, or in this case, alpha minus beta, I have to know the tangent of alpha, tangent of beta. Well, they didn't give us that. They gave us the tangent of beta, but they didn't give us the alpha, so I got to go use this to find it. On the sines and cosines, you need a combination of both. Where in the world are we? Right here. You need both sine and cosine of both angles. So essentially, you need to get everything there is about both of these angles. So how do we do this first one? I'll tell you where we go. We get sine of alpha equals 3/5, and we got to get a triangle. They tell us our alpha is between -3 pi over 2 and negative pi. So they made this not nice, but here's negative pi. This is -3 pi over 2. All of that fancy talk is to tell you we are in the second quadrant. That's my alpha. Okay, so remember, 3 pi over 2 is down here because you go 270 degrees around. -3 pi over 2 is back over here. That's why it was where I listed it at top. Okay, so all that to show that alpha is in the second quadrant. All right, and we then know, battery on my laptop's about to die. Let me get done with this real quick before I lose everything. Okay, so I'm going to talk while I'm pulling out my charger, so sorry if I'm far away. Let me know if you can hear me. But in our problem right now, we want to build that triangle for alpha and get everything there is to know. Know all 3 sides. That way we can get sine, cosine, tangent, anything that we need. All right? So I've got my line, and now I'm going to draw my triangle here. And because I know that sine is 3 over 5, I know that's a 3, that's a 5, and that's going to be a -4 when I do my Pythagorean Theorem. For the beta, I get tangent of beta equals -1 over square root of 3. So I got to know, again, what quadrant I'm in, so I get the right pluses and minuses. So they tell us we're between pi over 2 and pi. Well, we happen to be in the same quadrant here. There's beta. So draw your triangle. We get -1 over -3. Now this is the part that's interesting, is because it's y over x. Is it -1 over +3, or is it 1 over -√3? Which one do you use? This is why the quadrant is very important. When we're in the second quadrant, I know, let me erase some of this garbage here. I know that in this second quadrant, that's my positive, that's my negative. So I'm going to use this one. So it's a negative root 3 and a positive 1. Now you go get your Pythagorean theorem. Get 1 plus 3 equals r. R is going to be plus or minus 2, but remember, r's are always positive, so now we know the r. So at this point, if you need to find sine of alpha plus beta, look at your formula. I'm just going to pull this up so I don't have to write it. Sine of alpha plus beta is sine alpha, beta, cosine alpha, cosine beta. Go to each triangle. I'll get the sine of alpha from here, or I already knew it. I'll get the cosine beta from here, negative root 3 over 2. Cosine alpha, negative 4/5. Sine beta, 1 over 2. And now I'm done. When I do this tangent of alpha minus beta, I need to know tangent of alpha and beta. They gave us tan of beta, but they didn't give us tangent of alpha. I know it's negative 3/4 because I've solved for the triangle. So in any of these cases, this is what you got to do. You need to build your triangles. When in doubt, go build your triangles, and that's going to open up everything. So it's a combination. Build your triangles and then use your appropriate formulas. Okay, so for quiz 6, number 2, establish the identity. I'm going to look at this one and say, I don't like all this stuff on the right. So Jason, we're talking about which one's more complicated. I think the right side is double complicated because it's got a lot of stuff and it's got the half angles. So go pull up your half angle formulas, which remember the second things we learned today. Oh, not that one, sorry. A little further down wrong one. Today's stuff, near the end, the tangent of theta over 2, okay? Now notice, here's an interesting thing right here. I'm going to point out. We have tangent squared of theta over 2. This is tangent of theta over 2. All you have to do is square this, and now you have tan square of theta alpha over 2 or whatever. And then you square this. What's great about this is the plus minus goes away. It looks like this previous slide, remember? Come on, right there. This is another formula you can use. It's a better one right here. So see this tan square of theta over 2? You're going to use this one, and you're going to just go right to this. You don't need a plus minus. You don't need to identify the quadrant. You just need to write this, and then you're going to do it for the top and the bottom, and then you got to clean it up. And you see that's exactly what they're doing here. Find the choice that works best for you there. Okay, another preview here. This is just like the one we just did a minute ago. Answer is going to be pretty close. I would suggest removing the cosine of 2x and then rewriting that, cleaning it up, solve, get that c by itself. And if you do this correct, believe me, the entire trig functions will be disappearing. They will cancel themselves off. You're not going to get left with some x's or some trig functions here. Okay, now realize also, when you guys see this quiz, not everybody is going to see this same question for number 3. I have everything mixed up. So this number 3 might be number 3 for one of you, but it might be number 8 for somebody else. And this particular question has multiple options. So it might be for one of you, but someone else will get a different random generated problem. So you may get something that doesn't have this. It's just another identity or something like that. But if you had this one, this is what you would get. This is how you do it. Okay, so we did this one earlier today. Use sum or difference to find this. You get an option here. You can make either. So they give you a few choices. It looks like, okay, rewrite the trig function. So this is interesting. They want you to use either, but they're kind of forcing you into one. Notice they have a 120 minus 45 is the only way to get there. So you have to use a difference formula. Check your cosine difference formulas and you'll see which one of them it's going to be. It's probably going to be this third one right there. And then find the exact value. So it's a 2-step. Take the answer you get here. And this is the tough part, because if we were doing this as a homework problem, it would tell you if you're wrong and you'd fix it. But if you click B by accident and you start to do this one, B is wrong. And then of course, this exact value is going to be wrong here. So my hint to you all, when you do this problem and you plug in, the cosine of 120 and 45 and sine of 120 and 45, and you get your exact value, do that trick I showed you a few minutes ago where go plug in cosine 75 to your calculator. and write down that decimal, 0.2588. Now take the answer you got here, plug in the radicals and all that, see if it matches the 2588. If it doesn't, then that means you either calculated this wrong or you picked the wrong one up here. So that's my hint to help you out on number 4, if you had that one. Okay, use a half angle if you're not sure which one to use here. So 2 things. Number 1, let's make this a cosine. So it's 1 over cosine because we don't have half angles for the trigs. Remember, this is all we have. So if you're going to use this one, you probably got to use this one. And all that means is you take this answer and flip it over. It'll be the square root of 2 over 1 plus cosine alpha. Now, the part that's tough is when it's a half angle, we got to figure out what this is to make it half. Okay, so your alpha is going to be double this. So my alpha will be twice as much of this. So it's going to be 13 pi over 6. And then that's what we're going to use. And they even give you some hints on this one as well, what to do. Couple more here. We did one a little bit like this. Solve the equation. Okay, so when you solve it, you notice already, if this scares you, there's a lot of solutions. They give you 6 choices, and it looks like every one of them has 8 answers. You're going to get a lot. There's a reason why. You have to rewrite these as single thetas if possible. And that what my first suggestion is, let's crack this down a little bit. Let's use a half, knock this down, combine terms, try to solve it, but realize there's going to be a lot of answers here. Okay? I'll give you another hint. This is a backdoor hint. Okay? I don't like it, but if you're absolutely stuck, worst case, they all have a 0. I don't worry about that one. But I see that like this is the only one right here that has a pi over 3. Here's what I'm going to do. I'm going to plug pi over 3 into this problem, see if it works. If it does work, then I'm good. If it does not work, I eliminate C. So find the unique solutions. Like, see, they all have pi. Don't bother with pi. But only this one has pi over 3. Only this one, I think, has pi over 4. So try oh no, this one has pi over 4 also. Or a couple of them have pi over 3. But if it works, then you know it's either going to be F or C for the pi over 3. If it doesn't work, you eliminate those. So you can knock these down by process of elimination, but try to solve them first. Okay, definitely try that on the homework. So here we have one of these, it's kind of a word problem, but not really. We have an angle, and what it's asking is, what are they asking? Show that this equals that. And I haven't seen this one yet, so let me look at it here. Okay. So let me make this a little bit bigger so we can see what we're talking about here. All right. So they want you to rewrite tangent in terms of theta and theta 2. So look at our problem right here. And they want you to rewrite them. And we know that tangent equals all this, where we have the 2 slopes of the 2 lines. And lines are L1 and L2. Oh, and here's what we need to look at. Tangent of theta 1 is equal to M1, and then that one's M2. So remember how this works here. When we're looking at these two, this theta right here, you got to play a little bit of geometry, okay? So that theta is the same as this angle right down here. So I'm going to zoom in. I'm not really going to zoom in, but I'm going to look at the little triangle. This one right here, okay? That's the triangle that I drew. And if you're given this problem, the idea is that, okay, if that's a theta, that's also a theta, because they're vertical angles. This is theta 1. If this is theta 2, you know that this angle is going to be basically pi minus theta 2. It's the rest over. So that's what I'm talking about right there. So I know if I add all these up, I can figure out a few things to get theta in terms of the other two. Okay? So I know that theta plus theta 1 plus pi minus theta 2, all of that's got to equal pi. Because it's a triangle. I'm adding the 3 angles up. The pi's cancel. I get theta equals theta 2 minus theta 1. And that's the replacement. See if that'll push you along to the right area. And you see that's kind of how they're coming up with all this stuff right here. Okay? Now, This is probably one of the weirder problems on your quiz. If you get this one, I would suggest saving it to the end because it's going to take a little bit longer. And this is the case for all of them. Every quiz problem is worth the same amount. So don't spend 30 minutes on one problem when every other problem is going to be 4 or 5 minutes. If you see one that's taken a while, pause on it and come back. Because if you run out of time and you only miss number 7 because you ran out of time, then that's 1 out of 10 you lost. But if you spend all this time on number 7, then time runs out and you didn't even get to 8, 9, 10, you've lost 3, 4 points on that one. So keep that in mind. On this one, they didn't specify how to do it. They just want the exact value. Start looking at your double angle or your half angle formulas. Another thing I'll tell you is this is greater than 2 pi. So my suggestion first is subtract 2 pi from it. Bring this down to 1 pi over 12, and that's going to make it a little bit more clear. Number 9, we just did this one a little while ago. Alpha plus a beta. Or we did this the other day, I'm sorry. When you have 2 different inverse trig functions, each of these is its own angle. So then, like I did earlier today on this quiz, make 2 different triangles. And in the end, once you have your triangles made, this is what you're going to be finding. Okay, because it's this plus this. So once you have your alpha triangle, wherever that might be, once you have your beta triangle, wherever that might be, hopefully you've got all 3 values solved so you can find everything. Now, you use the formula and say, well, yeah, I know how to find alpha, cosine of alpha plus beta. It's cosine alpha, cosine beta minus sine alpha, sine beta. So you take the cosine and sine of this, you get the cosine and sine of that, and then you get your exact value. So that's the steps they're looking for on this quiz problem. And the very last one, what do we got here? Find the exact values. Oh, okay, same kind of thing. Build the triangle. You're given that secant equals 5, and they tell you that the cosecant is less than 0. So what that means is that it's just an awkward way of telling you where to build the triangle. They tell you that cosecant of theta is less than 0. Well, where is cosecant negative is what that's saying. Well, it's the same place where sine is negative. It's got to be one of these down here or here, okay? And then they tell you secant is 5. It's a positive 5. Where is secant positive? It's here and here. That tells me I got to draw my triangle in the 4th quadrant based on those 2 things. So there's my theta. And now secant is 5 or 5 over 1, which is r over x. Sorry. So my secant has an x value of 1. It has an r of 5. Do the Pythagorean to get the y. And now when you rewrite each of these 5 in terms of their exact formulas, they're going to ask for cosine and or sine of theta. We got them all from that right there. Okay, so hopefully that preview will help you out a little bit. Do your quiz. You got 2 tries. Remember, quiz 5 is due tonight, Friday night, June 24th. Quiz 6 is due on Monday night, June 27th. All right, that's it for the week here. You should be good to go on these. We will resume on Monday afternoon with these. And if you have any questions, let me know over the weekend. Have a good one.